Okay. Hello, everybody. And today is our great pleasure to give the presentation and tutorial on hybrid quantum classical computing for future network and optimization. And this tutorial will be given by Professor Lei Fan and myself. And we came from the engineering technology and electrical and computer engineering of University of Houston. And also thanks to our 3 students, Dongqi Zhao, Wenlu Xuan, and Mingze Li, and also thanks support from National Science Foundation. So here is the outline. First, we give the motivation and the quantum computing basic, and then there's a 2 mathematical and physics and background, which is ADI back quantum computing, hybrid quantum classical computing. And after that, okay, we will give several applications. And finally, we have the conclusion and reference. So let's talk about the quantum computing first. First, for the classical computing, it has been invented in 1945 based on the silicon. And after 80 years, and it's still very popular. But in 1980s, okay, firms say that, okay, maybe we need to use quantum mechanism in our computers. So after many years, okay, recently the quantum computing become such a hot topic that is probably the next big wave after this kind of machine learning. So then what is the motivation? Why we want to use the quantum computing? What's wrong with the classical computing? So let's consider this case. Suppose we have N guests attending a big party, and then we want to arrange the optimal kind of seat planning. So in this case, okay, the total combination is N factorial. So if we have a 2 total combination, that's okay, only 2. In fact, 2 factorial is only 2. However, if with a more kind of guests, only 5 guests, we need to have a kind of 120. And if we have 10 guests, it's more than 3 million combination. So in this case, okay, in the classic computer, we have to enumerate all these this combination, all these possible combination. So in this case, okay, the classic computation, okay, cannot handle this NP-hard problem. And this kind of complexity will go exponentially high with a number of variables. So in this case, okay, the classical computing have a very much bottleneck. And in this case, quantum computing give a huge advantage. And so this gives us some kind of similar things also happens in many fields. For example, life science. And recently there are a lot of big news about the AI-based kind of protein. And also for DNA, RNA, all this kind of different combination of what is the gene. And this is a huge number of combination. And also for the manufacturer logistics, who should I do first, who should I do next? And the financial service, there are so many stocks to invest. So all this computation need a lot of kind of combinatorial kind of optimization. And in this case, okay, classical computing can hardly handle when the for those NP-hard problem when the dimension is going high. However, for this kind of quantum computing, which can be achieve the same kind of thing by 3 steps. So for the first step, okay, the machine is active by creating an equal superposition of 2 N states. So basically on the left figure and the left part of the left figure, and you can see that, okay, on this kind of we have a N kind of qubit, okay, and then we create this equal probability, and so that, okay, all this kind of it's just like we create the parallel universe, okay, which with an equal probability of 2 to the power N state. So this state, before we do the observation, exists. And then the major problem is how to encode this kind of system with this kind of optimization by applying the apply gate or the magnet field into the second part, okay, in the middle figure. So in this case, okay, we try to transform the constraint optimization or the mixed integral programming or this kind of combination problem into this kind of into this kind of this kind of qubit state, so that okay, some of the state have a much higher probability than this kind of the other state. And then the third step on the right figure, the machine come to a solution by using the physical principle of interference to magnify the amplitude of a correct answer and shrink the incorrect answer. So sometimes, okay, we need to shrink iterative between the step 2 and step 3. So the step 3 is basically, okay, try to sample it. So we all know this quantum. In quantum, we have this kind of catch whether or not it's live or dead, right? Okay, before we sample it, okay, all those states, all these 2 to the n times, okay, for a parallel universe exist. But when we try to sample at step 3, okay, due to the work that we have done on the step 2, that the global optimal part will have the higher probability to get sampled. So in this case, okay, if we do the sample, then most likely, okay, we will get the global kind of optimal solution by the step 3. And also, okay, because some of the algorithm need to have the iterative, so maybe the step 2 and 1, 2, 3 maybe kind of need to iterate to do that. So this is a kind of strong power of this quantum computing. And then now the party seating have the 10 guests. So in this case, instead of 3 million one, and then we only need to 22 qubit to present this one. So in this case, okay, the complexity is much lower, and also okay, we just need to have one round and 22 qubit to generate the parallel universe in the first part, encoded in the encoded it with our problem, so that okay, the global optimal will have a higher probability in the second step, and then sample at the third step. In this case, we can get this kind of global solution, global optimal with high probability in one shot. So in this case, you can see that okay, this kind of for the quantum, it's a significantly kind of reduce this complexity. So I remember many years ago, there's a Nature paper, Science or Nature, I forgot. Okay, saying that okay, with quantum computing, okay, NP hard problem, NP will equal to P. So basically, you can solve any kind of NP problem using the quantum computing, and that is critical important because many kind of nowadays with so kind of powerful classical computer, okay, the major problem left for the scientific is this kind of NP hard problem. And for example, this kind of protein kind of things, or the DNA one, with quantum computing, okay, we can open a whole gate of the research. So that's reason, okay, with a new development of quantum and a new research gate is opening, and then probably that will be a next big wave for the research. Let's wait, maybe in 1 or 2 years, yeah, and everything will change a lot. Okay. So in summary, the quantum computer can create a vast of multi-dimensional space to deal with a large problem, especially those NP hard integral problems, and translate them back into what we can see. While the classical computer may have the difficult to do the same, because the classical computer have to do this kind of enumeration for this. However, it doesn't mean that, okay, the classical computer will be obsolete. And what we only mean that, okay, the quantum computer can do a certain job that the classical computer cannot do well. And then, okay, what we, in this proposal, in this tutorial, we want to study, okay, how could we utilize the advantage of both quantum computer and the classical computer, such that they can work together, so to solve a kind of a complicated problem that we face in the engineering domain. So this is the purpose of this class. And the quantum computer also have the limitation. For example, the number of qubits currently cannot be that large. So all these kind of challenge. So from my understanding, okay, the quantum computing and the classical computers will kind of coexist together and work together in the future, in a long near future. Okay. So okay. for quantum computing is booming, and you can see that, okay, there are so many kind of company like D-Wave and this QD Laser and some Cambridge and so on. So there are so many kind of top funded company, and then the global quantum marketing is growing exponentially. And currently, okay, the key type of quantum computing and their application and generality, typically we have three types of this quantum computing company. The first one is a quantum annealing, and the most representative one is a D-Wave. It's a very special form of quantum computing with an unproven advantage over the specific formula of conventional computing. So basically, okay, this kind of quantum annealing basically, okay, only work for a specific optimization problem. And then, okay, in this talk, we majorly concentrate on this quantum annealing part. However, they have a much more kind of qubit available. And the second one is analog quantum. And Infinite Q is a kind of a representative company. And the most likely form of quantum computing that will first show how true quantum speed up over the conventional computing. And the third one is this kind of a universal quantum, which look like IBM and so on. It's a true grand challenge in quantum computing. So it offers the potential to exponentially faster than the traditional computer for a number of important applications for science and business. So universal quantum, basically you can solve all kinds of different type of quantum problem. However, the number of qubit is very limited for this one. And then here is this kind of summary. So for the quantum annealing, and it can implement a lot of qubit. So the application is limited to the optimization. And for the other one, other application is very restrictive. And analog quantum is somewhere in the middle. So basically, application is chemistry, sampling, quantum dynamic, and the generality is partial. Well, for the universal quantum, okay, basically it's a crypto, search, and security computing. The general one is very high. So if the universal quantum is implementable, and then in the future, all this crypto kind of will be easily break down, and all this blockchain, okay, it's a kind of over, okay. So you can see that, okay, this is how powerful the quantum. So here, okay, it's a kind of, trade-off. You can see that, okay, for those, for the most simple one, okay, for quantum annealing, they can indeed have a lot of kind of qubit, 5,000. Well, on the other hand, for this more general one, they just have a dozen of this kind of qubit. So there's a trade-off. So in this talk, we can concentrate because we are more network optimization guy. So in this talk, in this tutorial, we concentrate on this quantum annealing by using the D-Wave. So, and specifically, okay, we want to have the quantum annealing. So basically, okay, in this kind of optimization problem, we will have many local optimum. If your optimization problem is a kind of non-convex, and also for integer program is makes things even worse. So classically, okay, we have this kind of simulated annealing by heating up this kind of, if the optimization problem is fall into the local optimal, it will heat up, and so that and then cooling down, just like the metal annealing, so that, okay, it can overpass this kind of local optimal. Well, for this kind of quantum annealing, all those local optimal before your sampling, okay, it's already exists there. Okay, so basically in the parallel universe, you have this different the local optimal coexist together. And then you're using this kind of mathematical and physics circuit, something like that, so that you make the probability of the different local optimal differently. The lower the energy, the higher the probability. And then at the end, you open the gate and try to do the sample. And the one with the lowest kind of the lowest kind of energy will have the highest probability. In this case, you can easily, with high probability, you can get the global optimal. So this is a basic idea of the quantum annealing compared with the classical annealing. Okay, it have a huge advantage. And the next, I will switch to Dr. Fan.
Yes, let me share my screen. Can you see my screen?
Yes, we can see your screen. Okay,
good. So here, let me introduce the adiabatic quantum computing. For as Dr. Han introduced, there are actually there are two types of the quantum computing. One is the circuit-based model. The other is the analog-based model. And here, adiabatic quantum computing is a kind of analog based model. And in this part, we will first introduce some basic concept of the qubits and quantum operations. Then we will introduce how the quantum algorithm solve the problem. After that, we will introduce this one very special kind of and powerful algorithm, quantum annealing algorithm. And after we introduce the quantum annealing algorithm, we will introduce how we apply the quantum annealing algorithm to solve one optimization problems. This kind of optimization problem is the quadratic unconstrained binary optimization problem. And this model is currently can help us solve some integer binary optimization problems. This is the overview of this section. And first, about quantum computing. Everyone talk about quantum computing. The true advantage in here is that for a bit, in classical bit, we know one bit can only represent 0 or 1. However, in quantum system, a quantum bit can be 0 and 1 at the same time. So we call it at the superposition. Here we can see on the slide that we define a quantum bit phi, and this phi equal to alpha plus 0 and beta plus 1. Here the cat 0 represent the bit is on the state 0, and this cat 1 represent the bit is on state 1. And alpha and beta are the magnitude of these two states, each status. And we can see the norm of alpha or alpha square represent the probability of the state on 1 and on state 1, and then the beta square represent the probability at this qubit on the state 1. So the total of the probability should be 1, right? Because you cannot, that's all the scenarios can happen. So this is one qubit. One qubit can represent 2 scenarios or 2 states. And then another important operation in quantum computing is this tensor product. Now we see 1 qubit can represent 2 states. How about 2 qubit? Here I use psi and phi represent the over status of 2 qubits. And this tensor product represent how they work with each other together. And we can see for psi and phi, if we represent this composite system in 2 qubits, and we will have 4 scenarios, right? And here we can see 4 scenarios are 0, 0, 0, 1, 1, 0, and 1, 1. And these are the 4 states the composite system can be on. And for each status, we have a probability with it, or we have a magnitude or amplitude with it. Here, alpha 0 represent the magnitude of the state 0, 0. and the alpha 1 represent the amplitude of the stator there 1 1. So same as previously, we say the total of the probability should be 1 because in this system there are only 4 possibilities, right? So alpha, the square of alpha 0 and the square of alpha 0 1 and the square of alpha 1 0 and the square of R11 equal to 1. That means the total probability equal to 1. So now we have 2 qubits, and ideally we want to have as more qubits as possible, so we can give a general representation that how about if we have n qubit, right? For this n qubit, here you can see we define this phi as the n qubit system, and this can be expressed in the middle as the sum of I from 0 to n, and the alpha I represent the amplitude at the stator I. So here we have for n qubit, I would say this is capital N represent we have the total should be the power of 2n total number of the stators, and for here the I represent the ith computational basis of the space, and alpha I is the amplitude of the ith computational basis. Now, once we know the representation here of the system, we can discuss the algorithm, the quantum algorithm. Essentially, at the very beginning, when researchers and scientists discuss the quantum computer, they want to use the quantum computer to simulate the quantum dynamics of the physical world, because it is very hard for quantum computer to simulate it is very hard for classical computer to simulate the quantum dynamics. So for quantum dynamics, one of the important equation is Schrödinger equation, right? So for this Schrödinger equation, it will represent or describe how the quantum system evolves from T0 to T capital T. And this follow up the equation. Here we have the derivative, the status here, the psi here represented the actual state of the system at time t, and this ht is a time-dependent Hamiltonian. This Hamiltonian in physics, it is the kinetic energy plus the potential energy. So it's represent the system status, and then the Schrödinger equation described how the state change respect to the time, and the right hand side of this equation is the Hamiltonian multiply the stator of the system. And here we need more notation. Is for these stators, if you imagine a physical system, we can use the matrix to describe the system. So the system have eigenstate and eigenvalues. So here we use the phi j represent the j's instantaneous eigenstate, and use ej represent the j's eigenvalue. So eigenstate and eigenvalue are very important information to describe the dynamic system, the quantum dynamic system. We will see how we use this Schrödinger equation to solve the classical problems. So how do we use the adiabatic quantum computing to solve the quantum problems? Actually, the idea is that how do we use adiabatic computing to simulate the Schrödinger equation. So for this kind of computing techniques, it utilizes the quantum mechanics like the superposition, entanglement. First, we need to prepare the system at the initial state, and we want to simulate the system, and so that the simulator can evolve or transform this system by following the Schrödinger equation, so that it can evolve to the final state. And this kind of quantum dynamic simulation process have the potential to speed up the computing process, like the classical computing process. The idea is that you can imagine we want to solve a classical problem. We want to map the classical problem into a quantum problem so that we can simulate the system and get the solution from the quantum system. And this kind of adiabatic quantum computing, the scientists already mathematically proved that this technique is polynomial equivalent to the circuit model. That's the reason we mentioned that at the very beginning, there are two types of quantum computing. One is the circuit-based model, like the digital or quantum computing, and the other is the analog quantum computing. These two, mathematically, they are polynomial equivalent to each other. And for this adiabatic quantum computing, scientists already designed some algorithms to solve some applications in the machine learning area and quantum quadratic unconstrained binary optimization model, and also some scientists use it to design the PageRank algorithm. So let's see how the adiabatic quantum computing algorithm works. As I said, the key idea is that we need to map the classical problem to a quantum problem. So in order to map the classical problem to the quantum problem, we need encoding the target we want to have. So to solve a classical problem, we want to find a solution to the classical problem. So in order to find the solution, we need an encoding technique to encode the target solution on the final state. Remember, when I say adiabatic quantum computing, it is used to simulate the quantum dynamic process. So eventually you will get a final state. So that means if you use this quantum computer to solve a problem after the quantum dynamics, you got the system on a final state. You want the final state be your solution. That's the idea. The key idea is that you use a quantum computer, simulate the quantum dynamic process, and the quantum computer will stop at a final state. And this final state can represent the solution, the target solution you want to obtain for your classical problem. And another encoding is that the function. So for the classical problem, first you want to have the solution, right? Second is that how do you describe your classical problem? You have a function, and for this function, we need to encode this function as the final eigenvalue of the final state of the quantum system. So you can see here that two parts, right? For the final quantum dynamic system, you have the final state and final eigenvalue. The final state can represent your target solution. and the final eigenvalue can represent your target function. That's the encoding part. And if we consider we want to obtain this to the final state and eigenvalue, what do we need? Others. So remember that in the Schrödinger equation, that to describe how the system evolved, we need the Hamiltonian of the system. So that means we need to find a Hamiltonian for the problem we want to solve. And this Hamiltonian, as we say, it is time dependent, right? We have an initial Hamiltonian and a final Hamiltonian. For us to solve a classical problem, we need to design the final Hamiltonian for this classical problem. So that's the first part. We basically, that in summary, that give us a classical problem. We first need to know how do we encode our target solution to on the final state, and how do we encode the target function or the function which describe the classical system in the final eigenvalue of the quantum system. And we also need to use find. Actually, this is a challenge part. We need to find a Hamiltonian to represent our classical system. And after we finish this encoding solution part, then what do we do? Here is the final part, right? The final state of the quantum system. Then in order to simulate this quantum system, we need to prepare the system at the initial status. So the same, we need to find the initial Hamiltonian of the system, and we need to design its initial eigenstatus. So that's the prepare of the quantum dynamic simulation. After we prepare the final status and the initial status, we can prepare the time-dependent Hamiltonian. As I said, we can see from the Schrödinger equation that the Hamiltonian is time-dependent. During we simulate the quantum dynamics, we need to change the Hamiltonian. So how do we design the time-dependent Hamiltonian? We need to follow up this convex combination function. For example, we have an initial status of the Hamiltonian and the final status of the final Hamiltonian. We can use a convex combination to describe the Hamiltonian at the middle of the simulation. After that, after we prepare this status and Hamiltonians, then what we need to do is that just throw everything to the quantum computer, and then the quantum computer will evolve the system, move the system from t equal to 0 initial and to the time int. Then after we simulate this, we can observe the final state to obtain the solution. So it's a kind of measurement. We measure the final state of the quantum system, and then we obtain the solution. That's the idea. Actually, this idea is at the very beginning, I believe it's 1990s. The scientists want to use how to use the quantum computer. This is the way they want to use the quantum computer. And let's see. This is a adiabatic quantum computing algorithm. Then a special case of the adiabatic quantum computing is a quantum annealing algorithm. Quantum annealing adiabatic quantum computing have a very strict conditions, like they require the closed system. Here, we relax some conditions and design the quantum linear algorithms. The scientists design this quantum linear computer. It can solve. It's a very special kind of the adiabatic quantum computer, but it is powerful now. This part is that the idea is similar to the linear algorithm, the classical linear algorithm. We heat the metal to a high temperature, then it will cool down to a low temperature. And for the classical simulated linear algorithm, it is a heuristic algorithm, and it's a random search method. For the quantum linear, it similar to the classical linear algorithms because it also a kind of heuristic algorithm, and but it utilizes the quantum character or dynamics, and it is a kind of relaxed quantum adiabatic approaches, and it works in a finite temperature and in an open environment. So it put less requirement on the environment. So for the quantum linear, compared to the quantum linear and the simulated classical linear algorithm, because the quantum dynamics, we have a superposition. When we have a superposition, and then it has a chance to pass the barrier or with some probability. So this kind of effect, we call it a quantum tunneling. So the good side of this quantum tunneling is that it can help us escape from the local optimum. Right? We have a chance to get rid of the local local optimal solution, so that we can find a better optimal solution. Most of the algorithms, optimization algorithm, stuck in the local optimal solution when the optimization problem is highly nonlinear, non-convex. Which has a lot of local means or local max. So for this slide, on this page, we explain how the quantum linear works. At the very beginning, we prepare the qubits, and so that they are on the superposition and entangled with each other. And then after we prepare this quantum the qubits, then we can run the quantum computer so that it can evolve to a final state. And for the final state, we have a multiple eigenstates. The lowest energy state is the target state we want to have. The lowest energy state or the lowest eigenstate, lowest energy eigenstate normally represent the solution. And the energy normally represent the eigenvalue represent the energy or represent our objective functions value. So in order to use the quantum adiabatic algorithm use this quantum linear algorithm, as I said, one important thing is that we need to design the Hamiltonian, right? So we need to design this Hamiltonian. For this quantum linear algorithm, we use Ising model to represent this Hamiltonian. For this Eason model, we can see that first, it has two parts. The first part represents the quantum bits, how it spin, and for the second part, we can represent how the quantum bits interact with its neighbors. And here, the sigma z represent the poly z operator. It's a matrix, and hg represent local pairs on this qubit G, and the capital J represent or describe the relationship between two qubits. It represents the coupling strength between the two qubits. Then you can say this, we will say this Hamiltonian Eason model can be used to describe the quadratic unconstrained binary optimization model. So for quadratic unconstrained binary optimization model, here we consider an optimization problem without any constraints, but our target, our object function is a quadratic terms. And X here represents the decision variable or binary decision variable, 0 or 1. Choose it or discard it. And this type of optimization model can be applied to the problems such as job assignment and task allocation and these applications. And this kind of quadratic unconstrained binary optimization model, normally they are NP-hard problem, unless you have a very, very special Q. Otherwise, unless you have a very special matrix Q. Otherwise, normally it is a NP-hard problem. And how do we apply the quantum annealing algorithm to solve this QUBO problem? The core idea is here. First, we need for optimization problem, for this unconstrained optimization problem, there are two things. First, the optimal solution for the decision variables. Second, the objective function. So we need to first encode the objective function as the eigenvalue of the ground state at the final state, the final ground state. And we need to use the ground state to represent the optimal solutions. So you can see here, we have H, the final Hamiltonian, and the object function fx, and the cat x represent the optimal represent all the optimal solution we want to have. And in order to convert the QUBO problem into the Eason model, we need some basic quantum operations. First, the sigma z is the poly z operator, which can, if we apply this operator on the stator 0 or cat 0, it will not change the qubit state. If we apply this poly Z operator to 1, then it will add a negative sign to this 1. And then you will see an interesting part is that for these two operations on the two different states, we can summarize as xg. This xg can represent 0 or 1. If it is 0, and we can generalize the equation as sigma z multiply this or sigma z apply sigma z on xg, then it will equal to 1 minus 2xg multiply xg. So notice poly z is the matrix. This matrix essentially is the mapping, and this xg, the qubit xg actually is a vector. So this matrix multiply a vector, you will get another new vector. So in order to generalize the vector 0 and the vector 1, we use 1 minus 2xg. This xg is 0, 1, a scalar value. However, this cat xg is a vector. So we still get a new vector, but this new vector's sign depends on the value of xg. If xg is 0, we can say we do not change the vector. If xg is 1, then we change the sign of this vector 1. So here, when I say status 0 it's a vector, and we can further define more complex operations. For example, if we have n qubits, right? For n qubits, we might want to only apply this poly Z operation on the jth qubit. Then we can see here we define the sum Z to J represent. In terms of this, we want to say, okay, we want to apply this this poly operator Z to the jth qubit, and all the other qubits on the system will not change. So this is a kind of operation. And similar, if we use this operator, this new defined operator, apply this new defined operator to xg, we will get the similar new vector 1 minus 2xg. So this is the findings we have. This finding can, or this operation can help us to build up the Hamiltonian. So as I said before, if we go back here, we can see this is the classical problem. This classical problem, what we have here is the Q, right? The Q matrix. So we need to use this Q matrix to obtain the Hamiltonian of the quantum Ethan models Hamiltonian. And then we can obtain this Hamiltonian. First, the initial status. The initial status is very simple. We do not change too much. We do not utilize the Q information. It's all this matrix. The Hamiltonian essentially is also a matrix. And based on the definition of the previous slides here, the sigma G to Z to J, we can define the initial Hamiltonian. However, the final Hamiltonian is the most important. So as I said, quantum adiabatic computing can solve different classical problems. the most important thing is that how do we encoding our classical problem into the Hamiltonian final Hamiltonian of the quantum adiabatic computing. So here we can see we have a very complex representation for the quantum final Hamiltonian. And on this complex of representation, we can see we define Kg and Gij. This Kg and the sum of the Gij, essentially we obtain this from the Q. This Qij is from the classical problem. So here you can see from the Q matrix, we first formulate the parameters Gij, Kg, and C, this constant number. And once we have the representation of the J, K, C, we can formulate our final Hamiltonian. So this is, once we have this final Hamiltonian, then it's very easy for us to solve the problem. Remember that our target is what? To solve our optimization problem, our target is to have the optimal solution and to have the optimal object value. So this optimal object value is the eigenvalue of the final ground state, and the optimal object function solution will be on the final ground state. We just do the measurement or measure the system or observe the system, we can get the optimal solution. So this is the part of the quantum adiabatic quantum computing. So this is the core part of the quantum computing. In the next part, let's show how do we combine the quantum computing with the classical computing. So at the current stage, it is very hard to use pure quantum computer to solve problems because the limitation of the hardwares, and essentially even that we already the scientists already prove that quantum computer is at least as powerful as the classical computer. However, in the past, I would say past 100 years, we built a very mature this classical computer. We can take advantage of the both kind of computers. So here we designed the hybrid quantum classical computing algorithm. The idea is that we need to look at the problem, then find a framework or algorithm to solve this problem. When we look at this framework, we will look at different parts of this framework and to think which part can be solved on the quantum computer more efficiently. For example, we know we already find many polynomial algorithms on the classical computer. So if a subproblem of our whole problem can be solved in polynomial time efficiently on classical computer, there is no reason for us to use the quantum computer. So we want to use the quantum computer to solve the subproblems which are very hard on the classical computer. So here in this section, we will introduce first we will introduce the framework, the hybrid quantum computer, quantum classical decomposition framework. Then we apply this framework to a important problem, mixed integer linear programming problem. To solve this linear programming problem, we change the Bender's decomposition algorithm. Bender's decomposition algorithm is an important a popular algorithm to solve large-scale mixed integer linear programming problem. So when we look at this Banner's decomposition process, we find that there are some part of the algorithm we can solve it on the quantum computer so that we can speed up the whole solving process. Then in the final part, we will introduce our hybrid quantum classical Banner decomposition for the mixed integer linear program. Okay, here we can see that the idea is that for this hybrid classical quantum decomposition framework, we can apply the mixed integer convex problem. So first, we need to divide the mixed integer convex problem into two parts. One is the pure integer part, which can be solved by the quantum computers. And then the convex continuous optimization part can be solved on the classical computer. As we know, convex optimization is an easy problem, and we have a lot of algorithms to solve it in polynomial time. And the idea is that we obtain the integer solution from the quantum computer and send the integer solution to the classical computer so that the classical computer can only need to solve a continuous convex optimization problem. And then after we solve this convex continuous optimization problem, we can populate or generate cutting plans or strong valid inequalities and send these cutting plans and strong valid inequalities back to the quantum computer so that it can further improve the integer solutions. So it's an iteration process. First, we solve the problem on the quantum side, then send the integer solution to the classical computer side. Then we get the cutting plans from the classical computer sent back to the quantum computer. Eventually, they will converge. So this is the idea of the hybrid quantum computer algorithm. Let's see how do we apply it to the mixed integer linear programming. Mixed integer linear programming is one kind of important technique in solving the real-world applications. So here is the mathematical model for the mixed integer linear programming. And we can see we try to maximize optimization problem. We have two types of decision variables, x and y. Here, x is a binary variable, y is a continuous variable. And we have a coupling constraints which couple x and y. Here we use ax plus gy less than equal to b to represent the coupling relationship between x and y. And normally, even you relax the x from binary to continuous, then you can solve a linear programming problem. Unless this problem is very special, then you directly solve this linear relaxation problem, you got the integer solutions for the whole problem. Then it is a polynomial can be solved. But in most of the cases, in most applications, the application do not have this nice characteristics. So we still need to solve use some integer solution algorithm to solve this problem. This kind of problem is a NP-hard problem. It is very challenging. So let's see how do we solve it more efficiently. In 1960s, the scientists propose the Benner's decomposition. The Benner's decomposition idea is that we can divided the problem into two parts. One is the integer part, the other is the continuous part. We can first solve the integer part to get an integer solution and send it to the continuous part, then solve the linear programming. Linear programming can be very well solved on the classical computer. Then we can generate Benner's code back to the Benner's decomposition, the master problem. Here we can see that if we consider the left part is the original mixed integer linear programming problem, and we want to divide it into the master problem and subproblem. The master problem, if we use ZLP represent the optimal function of the subproblem, or we can represent the HTY part. You can imagine that it's a kind of two-level problem, right? You solve the problem X. Once you get X, then you can solve the problem ZLPX. This ZLPX is parametric by X. So once you know X, you have another linear programming problem. So that's the idea. We have this decomposition. So the original problem can be divided to a master problem and a subproblem. And this subproblem, normally we will use its dual formula because it can easily help us to get the extreme point and extreme ray. So you can think about this idea is that look at the top right formula. This top right formula, ZLP. ZLP is a function, right? This function is not a very simple function like a quadratic function or something like that. This function is an optimization problem, right? This function is an optimization problem. For this function, there are two ways to represent this function. One way is that we use this optimal model to represent this function. Another way is what? Another way is that we can represent this function as a polyhedral. This polyhedral have an extreme ray and extreme point. That means in order to describe this function, you need the extreme ray and the extreme point to represent this function. Once you get the extreme ray and the extreme point, then you can represent this function. So this is the idea behind the Benner's decomposition. It's like first we divided the problem into two parts, master part and subproblem part. This subproblem can be represented as a polyhedral. So the question comes is that how do we obtain the polyhedral representation of this optimization problem? So in order to obtain the extreme rays and extreme point, one way is that we can solve the dual problem of the subproblem. This U represent the dual decision variables. And if we can find the extreme points, and because the linear programming satisfies the strong duality, right? It is strong, satisfies the strong duality, and we can get the extreme point and extreme rays. And for the extreme points is that if we can solve the subproblem, get the feasible solution, then we can find the extreme points for this U. If the sum problem is infeasible, then the dual of the subproblem will be unbounded. So for unbounded problem, we can get its extreme rate. So the commercial linear programming solvers can provide us the extreme point if the subproblem is feasible. And if the subproblem is infeasible, and then this linear programming solver can provide us the extreme rates. Once we have this extreme rate and extreme point, we can use it to describe the polyhedral. And another terminology that we call it cuts, right? For the extreme points, actually it helps us populate the optimality cut. It can help us improve the optimal solution for the master problem. For the extreme rate, it populates the feasibility cut. It can help us reduce or get rid of the infeasible integer solutions. When we say infeasible, is that this integer solution will cause the subproblem infeasibility. So we want to cut off this infeasible points. So we need to use the feasibility cut as represented here. And we use the optimality cut to cut off the integer solutions, which is not the optimal integer solutions. So these two types of cuts are very important. And when we implement the Bender accommodation, we will see that normally at the very beginning of the stages, we get most of the integer solutions are infeasible integer solutions. We will populate a lot of infeasible feasibility card for the master problem. And then at the later stage, we can find feasible integer solutions, but we still need to cut them off because they are not the optimal integer solutions. So for this Bender's decomposition, we can use this. Suppose we introduce a variable t to represent the value of the objective value of the subproblem, and then this master problem can be described in the way at the bottom left. And here we can see in the master problem, we have two type of variables. First is the integer binary decision variables x. Then another one is the t. This t represents the objective value of the subproblem. And then we can use the iterative process to solve the problem. First we solve the master problem and send the solution x to the subproblem, and the subproblem will give us the extreme rate and extreme point. We can populate new cuts and add the new cuts to the master problem, resolve it. So this is a Bender's decomposition. We can say the master problem actually is very close to a pure binary programming problem. The only challenge is that we have a continuous variable t, to which is due to represent the object value for the subproblem. So this is the whole process. How do we solve the how do we implement the Bender's accommodation? Let's see how do we embed the quantum computing into the classical Bender's accommodation algorithm. So on the top, we can see the Bender's decomposition process is that we solve a master problem, then solve a subproblem. Subproblem is a pure linear programming problem. We do not need to worry about that part. The challenge part is this master problem. This master problem is a mixed integer linear programming problem. If we discard T, then it's a pure binary programming problem, right? For this pure binary programming problem, we can reformulate it as a quadratic unconstrained binary optimization model if we add penalty to the object function so that we can move these constraints to the object function. And here, T, another remaining challenge is T. We know T is a continuous variable, right? In order to use the QUBO model, we need to solve this issue. It's a continuous variable. The trick we play here is that, as we know, in classical computer, there is no continuous numbers, like continuous numbers. Like in the programming language, we define like float, double, but for digital computer, it only have a 0 and 1, right? So it only has 0 and 1. So the trick we use it here is that we can use the binary encoding, or use a binary to represent this continuous variable, right? So that's how we reformulate, how we make sure the master problem is a pure binary problem. So you can see here we introduce 2 to utilize 2 to represent the numerical value T, so that it can be a binary representation for this numerical value. Once we use the T in the binary representation, then the master problem becomes a pure binary programming problem. Then we can further convert or move these constraints to the objective functions by adding penalty cost, so that this problem becomes a quadratic unconstrained binary model. In order to move the constraints to the top of the objective functions, we need to add penalty cost and introduce new slack variables. And for some easy constraints, like on the table here, we can easily reformulate the constraints. For example, here, if the constraint is x1 plus x2 equal to 1, then we can use x1 plus x2 minus 1, then add a square to represent this constraint. Similar, we can convert the constraints with the right hand is 1 to a new formula. Basically, it is relatively easy to handle the constraints whose right hand side is 1. We do not need to introduce new slack variables. Here you can see we can easily convert it to quadratic terms. And then if the right hands of these constraints are not 1, then we will be in trouble. We need to add some slack variables so that we can convert or move the constraint to the object function. So this part is for the constraints whose right hands are not 1, we need to design the new object function more carefully. So once we move the once we use the binary representation for T, we can rewrite the master problem in the binary programming model, and all the optimality cards will be transferred to a term on the object function, so that we can make sure the master problem is unconstrained binary optimization model. So that's the idea of the hybrid quantum classical banded decomposition. Let's make a summary of that idea. Is that first, we use banded decomposition so that the banded decomposition can be divided, can use the banded decomposition to divide the problem into master problem and subproblem. The subproblem is a linear programming problem, which is very easy solved, can be solved. And the master problem, we have a very close to pure binary constraint optimization problem. We have a continuous variable T, and we replace this T in a binary representation, so that then this problem is a pure binary optimization model. And once we have this pure binary optimization model, we can reformulate as a constraint, unconstrained quadratic unconstrained binary optimization model by move the constraints to the object functions. And these object functions have the penalty terms, so that the optimal solution, the solution we get, will not violate the constraints. So this is the core idea for the hybrid classical banded decomposition algorithm. And here we show a simple example on how this algorithm works. And yeah, this example will show that how we add the cutting plan to the master problem and how the bound converge. The bound, how the I would say the subproblems object value converge. So this is a very tiny example show that hybrid classical quantum computing works. Now let's discuss the applications. I would handle this to Dr. Han.
Can you see my screen?
Yes, we can see it.
Okay, it's also moving, right?
Yeah.
Okay. Okay, and well, thanks for giving us a very solid kind of physics and mathematical background for this one. And now let's come back to several kind of applications that in the networking or this audience here. And we will talk about three applications. The first one is about the optimization problem for data center in energy, data center energy managed system. The second one is on this kind of in the wireless network, some certain optimization problem. And finally, okay, Dr. Fan will give us a presentation on the quantum machine learning part. So first, let's talk about this this kind of scheduling of data center and HVAC load in this kind of using our proposed kind of method. And in a data center, okay, basically, okay, it's consumed a huge amount of data, energy, and basically, okay, the data center use more electricity than the entire country. So basically, you can see that, okay, the data center is more than Africa, more than this Egypt and South Africa, and it will growing more and more for that. So in order to kind of reduce this energy consumption for the data center is also very important. And moreover, okay, even though a lot of places for this kind of blockchain and Bitcoin, okay, it's not allowed in many countries, but overall, okay, this kind of digital currency will also cost more and more energy for this data center. And then the scheduling of the data center and HVAC load. And basically, okay, we have data center, then we have this kind of the different pump, chiller, and tower, and basically try to and also we have this kind of energy from the outside grid, and also we have the renewable energy like the solar, and also we have the battery. So the key question is that, okay, how could we kind of exhaust the air and outside and data center and inside air so that, okay, we can control for that. And one of my former students, okay, maybe 10 years ago, worked on this smart building regarding the air condition as well as this carbon dioxide kind of comfortness. And then he used a dynamic control and dynamic game for this kind of optimization. And later, okay, she worked for this kind of Walmart. And obviously, okay, Walmart have so many kind of shops around, and how to control the air condition and the carbon dioxide for this ventilation is also a critical important. So our proposed approach is not limited to the data center, can also for many grocery store and many kind of logistics store storage as well. And here we have the problem formulation. We have the binary part. For this decision variable, we have the battery charging at the time, battery discharging, and chiller working and the cooler tower working or not. So those one are on-off control. And also we have the continuous decision variable. So the battery discharging power, battery charging power, and the battery status at the time t and temperature, and the AC temperature and the ventilation, wind speed, all those can be controlled in a kind of continuous. And you can see that, okay, this is a control variable, so those can be definitely mixed with an integral part as well as a continuous part. So this fit or this hybrid quantum and classical computing optimization well. And then the list of the problems parameter and the index and the set. So we have the time, and we have the zone for the data center. We have the available chiller in the data center. We have this available cooling tower in the data center and adjacent zone to zone. And for the binary decision set, we have this kind of put all the previous together continuous set look like this one. And then we have the parameter. So we have the temperature, battery discharging efficiency, battery charging efficiency, battery upper bound and lower bound, and the coefficient for cooling, and the first coefficient for window power state, and all this coefficient for pumping state, chilling power, and tower power size. And also we have some other parameters. We have the water, heat, and the electricity, server state, and solar, and so on. And also we list all these things together. So all these things can be a kind of complicated constraint and the parameters for this. And here we have this kind of outside air flow, return air flow, and supply, and the termination. And in the middle, we have the intermediate variable, like the charging of the battery power to preserve electricity relaxed by the chiller, and the grid electrical required, and HVAC is required kind of electricity, and pump required, tower required, and vent required, and also the total thermal load, and so on. So the we formulate the mixed integral linear programming problem, and we minimize under those kind of continuous and integral optimization for the objective function. The objective function is to minimize the total cost for the electricity imported from the grid, so that we can reduce this power consumption and also the cost, as well as a more kind of green, more kind of reduce this kind of carbon dioxide. And then, okay, we have this kind of constraint for the total, and this is the Geroff law and energy consumption and total sum of this kind of energy constraint, battery discharging law, battery status T, and battery kind of requirement, initial configuration, and the upper bound and lower bound, and this cannot be discharged at the same time of the interval, and also the average zone data, and DCRC network temperature linear state space model, and upper lower bound required for the room temperature, and upper lower bound for the room AC temperature. So all those are the constraints. And here, okay, let me give a joke. And in South Korea, okay, during the summer, okay, they have the smart building, so that, okay, the AC will turn off when the temperature is lower than 25 centigrade. So when I was in the South Korea, we will have the lamp and electrical lamp, turn it on next to the sensor, so that, okay, the sensor feel that it's more than 25 degrees, so the air condition will continue to work. I'm just joking, okay. Anyway, and we have other constraints like the minimization venting, airflow speed that come out of the AC, the minimization capacity chilling water, and the minimum capacity for the condensed water, the sum of heat load, the minimized amount of chilling water, the minimum amount of condensed water. And there are many other ones, upper bound for the battery, upper bound for the battery discharging, and the battery will not charge at the same time, and so on. And finally, okay, no matter how, okay, how many kind of constraints, we formulate this one as a mixed integral linear programming. And again, okay, follow the Dr. Fan's presentation on the Bender decomposition. The overall big optimization problem, no matter how much you have a integral and a continuous variable, and then all the other constraints will be condensed into the big matrix of A, G, and D, and so on. So in this case, okay, follow the same step. We have the linear programming kind of replacement. And then, okay, for this kind of ZLP, we can represent this one. And then we have the LP duality to change this one. And then, okay, the hybrid quantum classic Bender decomposition will have the algorithm like this one. So basically, okay, for those integral part, we will using this quantum computing to do that. And after that, the integral programming solution will provide to the classic computing for this continuous optimization. And each iteration, we will provide more kind of, feasibility card to this sub problem, to this kind of continuous kind of problem, so that this kind of searching each time, okay, this sub problem will provide more feasibility part for the master problem, and so that, okay, the searching problem will become smaller and smaller. And here, okay, we have the experiment, and then we have this. This is a specific algorithm for this kind of quantum part. We have this the bit to assign the decimal part, but the bit assigned to this integral part, and so on. And also we have the threshold. The reason to set those one is that, okay, for the current kind of qubit, for the current the maximum qubit available for this the D-wave is limited. So this is how we set up for this quantum part. And then we discuss the three cases. And then this is a setup for these different three cases with different binary variable and iteration. And here is a case for the different matter and different setup. So the hybrid quantum classic Bender decomposition, and we can see that it could save 40% of iteration than the classic Bender decomposition. And also here is the result, and here is the iteration, and then we can see that the proposed one with several iteration will converge to the optimal solution, while for the classic one will take a longer time. And this is for 4 different cases. And then, okay, we can see that the hybrid quantum classic vendor decomposition take a lead for the beginning and to win the comparison for the safe and sound. So in other words, okay, not only we fastly convert to the global optimal, but also, okay, it can ensure to the global kind of optimal. So this show us the advantage of the proposed algorithm and for such kind of situation. So this is kind of the data center, and then the next problem is for the optimization problem for wireless network problem, and a lot of paper for wireless network can be formulated as constraint optimization, and in this kind of example, we show this kind of network virtualization, and as an example, and other method can be extended in a very similar way. And here for the traditional network, we have all these kind of devices. So basically, okay, basically belong to the same identity. For example, okay, if I want to make a phone call through the Verizon, then okay, all these kind of the Verizon will take the lead as a master, and then try to find the route to the end. And so basically, one company tries to own a lot of kind of equipment, and the network function virtualization. Well, basically, okay, they can have all these functions as virtualized. So the service provider, instead of own all these kind of components, will try to kind of find this kind of available resources on the net, and then try to utilize them, and then try to kind of satisfy the user's requirement. So this is a kind of a network function virtualization. So in other words, okay, when you see the base station around, it either belong to a Verizon or AT&T, but in the future, maybe I can set up an ugly base station at my backyard, and then I can try to sell my service, virtual service, to either different company to make money. So this makes the network very flexible, and the cost will be lower. And I remember that, okay, before the COVID, I went to South Korea, and they are very popular for the network network virtualization. And I talked with a lot of hardware engineering there, and they told me that, okay, this is a software company try to invade the hardware company again. Okay, anyway, so this is a kind of background. And here, this is a virtual network function implemented in the virtual machine. So basically, we have a different virtual network. And so in order to implement, for example, if I want to make a phone call, and then, okay, the system will try to find the available resources on the physical network, and then try to set up a virtual network, such as, okay, they select this kind of available resources into the different physical network and set up a virtual network to implement the user's requirement. And so by doing this one, okay, the virtual network function manager try to orchestrate all these kind of virtual resources to do this kind of requirement by mapping the virtual network to this physical network. And so they have the challenge is that, okay, they have vast service chain, and also it's a very kind of a scheduling problem, how to deploy the virtual machine to persist this kind of virtual network function. And also we try to do specifically, we try to do the delay minimization. So this is a requirement. And so here, for a specific model, we assume all the hardware is located in a data center. So this is a kind of a limited kind of scope, but you can extend this work into a much more variety. And then we try to neglect this transmission delay. And here TJM is a minimum integral that equal to or larger than this kind of thing. So basically, okay, we have 3 virtual machines, and then they have the different kind of task function. And then, okay, for the different things, okay, they need to kind of implement this function over the different time. And then they have the dependence, okay? So you'll have to implement one earlier than the other. And then this is the total time slot. And then the key question that, okay, how those virtual machine can be implemented, those kind of this function, such as the overall time slot that's needed is minimized. So this is quite an integral programming scheduling method. And then here we have a decision variable, which Xij is equal to 1 when the virtual machine M is used to processing the function of Fijk, otherwise it's equal to 0. And then this Yijm is equal to 1 is virtual machine M is used to processing this one. Fijk in the time slot T. And also we have Z and P. And we also have some other variable for this function to have a certain constraint and so on. And so here we have the pure integral linear programming method. So here we have this kind of this objective function is minimize the total delay of all service chain in the network. And then we have the different constraint again, calculate the first time of any service chain. Any function can be processed only on one virtual machine. And if and only if a function is allocated to virtual machine, this virtual machine can start this at some point. And each virtual machine can be processed at most one function in one time slot. The relationship between these different kind of X and Y. And also we have the required total T for the processing function must be satisfied those constraints. And the total relationship between this Y, Z, and P. And once the virtual machine starts the processing, and must be satisfied for this manner. And the next function for this service chain must be proceed after the processing of one before the other. And also, okay, Fyzp must equal to Y if equal to 0 if VP cannot process the function. And for any function F, only one Z and one P can be equal to 1, and so on. So in this case, okay, we try to, formulate this one with QUBO. So basically, okay, we formulate this one without we put this one, we map all those constraints using this kind of equivalent penalty into this kind of QUBO method. And so we transform the previous kind of integral linear programming, constrained integral programming into this QUBO format without constraint. And here is the overall algorithm, and find a reasonable Tmax and reduce the number of variables and solve the problem with more variable. So in this case, we use a D-Wave solver to solve this QUBO problem. And here we have the different setup and with a different parameter, with spending much longer time to finding the feasible solution for the case F. For case F, the size value rate is very low. So basically, okay, the matrix Q size increase, the difficult to find the optimal solution increase. So basically, we can see that, okay, by setting up this kind of accurate kind of number, and we can kind of, by carefully satisfy this kind of matrix size, and we can achieve this kind of successful rate. And in the other cases, okay, we cannot, but we need to carefully set up clearly, okay. And anyway, okay, and I think I have a stop here, and Dr. Han will continue.
Can you see my screen?
Yes, we can see.
Okay, good. So in this part, we will introduce one more application in the how do we solve the machine learning related problems by using the quantum techniques. And for the classical machine learning, we know it takes a lot of time to train the models, the machine learning models. And by the way, that for machine learning problems, essentially it needs to solve the optimization problems. Here we want to take the advantage of the quantum optimization algorithm to help speed up the machine learning training process. And this problem we solve is the feature selection. So for the machine learning problem, we need to identify the key features. Right? If we have many features to learn, then it consume a lot of time and resources. But if we only keep a minimum, only a very few features, then the machine learning model may have a very bad performance. So that we need to balance the number of features so that we can save our training time. At the same time, we can have a good performance. So for the features, there are relevant features, irrelevant features, and redundant features. For us, we want to get rid of the irrelevant features and keep the relevant features. And we want to reduce as more as possible these redundant features. And at the same time, once we get our machine learning model, we can still have a good performance and avoid the overfitting issues. That's the key idea. So you can imagine that the feature selection problem is a decision problem, right? The question is whether you want to keep this feature or throw it away. So this is a binary decision problem. And for this binary decision problem, we can design its objective function as shown here. First, we use X to represent whether we keep this feature or not. Then if X is 1, that means we keep this feature. If X is if Xi is 0, that means we discard this feature I. So on this objective function, we want to minimize or we want to maximize the influence. So that means we want to minimize the negative of the influence. If we choose a feature, we hope this feature can bring in more influence to the system. So here, the IFI function represents the influence brought by this feature I. For the first part of this objective function is the independence relationship between the two features. So we want to minimize the relation, the features, the overlap of the impact between two features. So we want to minimize the number of the redundant features. So, and on this objective function, we can see we have a coefficient alpha. This alpha actually balance the two parts. One part is we want to like keep as more influenceable, as more features who has big influence on the system as possible. And at the same time, we want to discuss as more as the redundant feature as possible. So this is the balance between these two terms. And another key parameter is here, the key. Key represent how many features do we find. So this one is we need to use like a hyperparameter algorithm to find the preset key. So suppose we have like 1,000 features, we only want to keep 100. So this key is 100. But in order to find this key, we need to design a wrapper method to help us find the number of features we want to keep. Once we know the number of features we want to keep, then we can design the optimization model to help us find these key features. When we design the optimization model, we are not only use the model with objective function, we still need to consider the constraints. The constraints can represent the relationship between the different features. For example, some group of constraints, some group of features, they have conflicts. That means if we keep feature I, then the feature J will be discarded. So this kind of confliction should be enforced in the constraints as shown here. The sum of these features variable less than equal to 1, we at most we pick up one of them. We will not pick up 2 or more of these features. And some conflict means if I pick up I, then I cannot pick up J, or some rely on others. Like if I pick feature I, then I must pick up feature J. Here we represent this relationship as xi is less than equal to xj, which represents the rely relationship. And some features have are very important features. They have higher priorities. In order to ensure that we can choose these features, we can add a constraint like here, sum of the decision variables of these features equal to t. That means in this group, we need to pick up t features from here. So you can see all these relationships are binary relationships, right? We only use the binary optimization model to represent this feature selection problem. And this binary programming model can be transferred to a QUBO model. And the transfer process is that first we need to use the function I, the influence function I, to represent the Q matrix in the QUBO model. Once we have this Q matrix, then we can represent the Hamiltonian in the Ising model. Then we can shift this Ising model to the DWIP machine. The DWIP machine will map the Ising model to its own hardwares. And here is the flowchart of our proposed algorithm. You can see at the very beginning, we need to pull the data from the database and then pre-process massage the data. And then we select the alpha, the parameter, the weight between the two terms on the objective function. Then we update our parameters. Then we call this orange box is the part we formulate our optimization model. And once we formulate our optimization model, we can reformulate as a QUBO model. And the QUBO model can be sent to the quantum machine and solved by the quantum linear algorithm. And once the quantum linear algorithm solves the QUBO model, we can get the feature subsets which we like. And then we can use the select features to train our classification model. So this is the process. How do we implement our algorithm? And when we formulate one important, when we design our algorithm, one important parameter is the alpha. How do we choose the weight for the importance of the features and independence between the features? So this, we design a search algorithm to search this alpha so that we can balance these two important terms. And in addition to run our algorithm, we also need to find the best key. So how many features we want to keep in our system. So this key is the number of features. After we design our algorithm, we run the simulation and get result. And in order to compare our algorithm with other algorithms, we propose 3 criteria to evaluate the performance of our algorithm. The first one is accuracy, the second one is pricing, and third one is recall. In order to define these 3 terms, we first need to define the true false. Essentially, is that when you do a classification, that you might, for a true sample, for a true, you might give a false label. For a real true, you might give a true label. For a real true, you might give a false label. For a real false, you might give a false label, or for a real false, you might give a true label. So this is the 4 different scenarios we will observe after we training our model. So in order to evaluate the training model, we use based on this true and false, we design these 3 parameters. So the first one is the accuracy, which represents the percentage of how accurately we predict the samples to all samples that were forecasted. For the precision, it represents the capability of a classification model to identify the relevant data points. For recall, it estimates the ability of the model to discover all the relevant data points. Here, we compare our proposed algorithms with 4 different algorithms. And these 4 different algorithms have been applied to these feature selection problems. And on the top of these slides, we can see there are 3 figures. And each figure measures the performance of our algorithm from one perspective. For example, the first one is the accuracy. Second is the present. Third one is recall. And the bar represents the score we for each algorithm obtained. And the different color of this bar represent different algorithms. And the quantum QFS represent the quantum feature selection algorithms proposed by us. And we can see in the most of the time, this QFS have a very good performance under 3 different perspectives, all these 3 perspectives. And the time. So for the time, as we said, why we do feature selection, essentially, we want to save the training model. And also we want to do not spend too much time on the feature selection. So for the feature selection here, the first graph on the left shows the time spent to select the features. We can see compared to the other 4 algorithms, our quantum feature selection only consume around 700 seconds. And for the training, after we use the feature we obtained to train the classification model, and the classification model only need 25 seconds to solve the problem or give us the result. The time we spend training is much less compared to other algorithms. For example, here the HHO algorithm provide the features, and the training based on the features provided by HHO takes 70 seconds. However, the training model takes only 25 seconds based on feature provided by the quantum feature selection algorithms. So we can see that if we choose the quantum algorithm, the quantum feature selection algorithm, it can save us a lot of time. It can save us the selection time, and it also can save us the training time. So for the summary is that here for the evaluation method, we evaluate this method from 3 perspectives. We can see our quantum feature selection have a better performance compared to all other classical algorithms, and also compared to the other classical algorithm here, it is much more easy for us to find the optimal solution at a shorter time. At the same time, our quantum feature selection algorithm provide a better feature subset, or we remove more redundant features, and this help to save the training time for the classification model. So we can make the conclusion. Here I will shift the time to Dr. Han.
Okay. Allow me to share the screen. So you can see my screen, right? Okay. Can you see my screen?
Yes, we can see it.
Okay, and finally we have the conclusion. And for quantum computing, okay, there are a lot of kind of, the majority is still in the physics part. And typically, okay, they have 3 types. There's a universal quantum, and analog quantum, and quantum annealing. And then universal quantum, okay, have a advantage that it can solve many kind of astonishing things. For example, all the security, all this kind of crypto key, okay, can be solved with quantum, universal quantum. However, the number of qubits available is still limited. And on the other side of the spectrum, quantum annealing have a lot of bits, 5,000 or something like qubit 5,000. However, this kind of a solution is limited to a certain QUBO model, which is a kind of annealing problem. And in our talk, okay, we have this kind of, we have this kind of try to understand this QUBO model, try to link from the physics to this kind of algorithm. And moreover, we extend this QUBO model to this kind of Bender decomposition so that, okay, it can link this classical model, the classic computer with this kind of, with quantum computing. And then we show the 3 examples. The wireless network and the machine learning is still a QUBO model. And for the pure integral programming, and for the DC power kind of for the power management for data center, we have this Bender decomposition one for this kind of how to decouple this. And then, okay, I know that there, so basically, okay, you can think about this like this Doctor Strange, okay, this movie. So basically, he can calculate all the different combination, and then the art here is that, okay, by using the math and the physics for the digital circuit, for the quantum circuit, we can, for specific mixed integral linear programming, we can add the different weight and energy into the different type of solution. And so that, okay, the global optimal will have the lowest energy. And then when we do the sampling, then the global optimal will be sampled with a much higher probability. So in this case, instead of using this instead of using this kind of enumeration by the classical method, we can use in quantum, like this Doctor Strange, to find the solution immediately. And also, okay, because the current limitation of quantum computing, and so it's basically it's typically work well for this integral part. Well, for engineering problem, we have this kind of mixed integral programming with a lot of continuous variable as well. Well, for the classical computer, okay, continuous kind of variable have a very good solution like those convex optimization. So our question is that, okay, why not we can combine the classical computer with this quantum together? So that's the reason we propose this Bender decomposition to link those two types of computing together. And also we know that there are so many experts here, and we indeed eager to find the collaboration. And here is a related kind of reference, and thank you very much. Okay, so let me stop recording.